All right, resistors that are connected at both ends. So here's a resistor, and here's a better run resistor, and they are connected at both ends, are said to be in parallel. Usually we'll have a branch like that. And we say these are in parallel. By the loop rule, they must have the same voltage difference. Also, because any path we take, we know that the voltage is path independent. So if I go this way, or if I go this way, I have to have the same voltage drop because it's path independent, which means that they must have the same voltage drop across themselves. All right. Of course, by the junction rule, the inbound current has to split into, let's say, I1 and I2. And that means, since we're replacing this with an equivalent resistor, there would be an equivalent current. And we know that the equivalent current, of course, is whatever was coming into where our junction would have been. And it has to be, by the junction rule, the sum of these two. So the equivalent current is the sum of the actual currents that flow. But the equivalent current, of course, is the voltage drop across the thing divided by the equivalent resistance, and likewise for the other two. But they all have the same voltage, so we can cancel that. And we get this sort of interesting and vaguely familiar thing, which is that in parallel, the resistors add inversely. We add the reciprocals of their actual values and then take the reciprocal again. Textbooks really, for whatever reason, like to combine this and say, oh, so the equivalent resistor is something like R1, R2 over R1 plus R2, which is what this ends up like. That's the same thing, but I find that far less useful. It's easier to say that the reciprocals of the resistances add to become the reciprocal of the equivalent resistance. Also notice that just mathematically, this means that the equivalent resistance is always less than either of the input resistances. That when you add two things together, the total goes down. And you might find that a little weird, but it comes down to that you've added extra paths. So it is easier for the electrons to move through, because if they get sort of jammed up going through this one, the next one can shunt over to this side and go through this side. And so it's easier for electrons to move through the pair than if they were either one of them just there. All right, so question. When the switch closes, what will happen to the battery current? When the switch closes, we know that the equivalent resistance goes down because we have added two in parallel now. So the battery will draw more current from the battery because, of course, we'll have something like that the current is the EMF of the battery over the equivalent resistance of the circuit, the new equivalent resistance circuit. Before we throw the switch, the equivalent resistance of the circuit is just R1, so not that interesting. When we throw the switch, we decrease that denominator, and so we increase the current. All right, the three bulbs here are identical and the two batteries are identical. Compare the brightnesses of the bulbs. Here you want to be very careful because this looks like a problem we did earlier but isn't. I'm going to draw the diagrams for each. In case A, we have EMF source hooked into resistor A. That's circuit A, no big deal. In case the second case, case BC, we have EMF source, and then it comes and it splits. Notice that the current splits here and here. So we are in a parallel circumstance where we have resistor B and then resistor C. Notice the equivalent and probably more common way of drawing this would be to put them just side by side. So ba 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 for B, and then same for C. What we can see here, though, is that the voltage difference that they draw in case A, remember call this case BC. In case A, if we take from here to here, that voltage is the same for B and for C. So all three of them are undergoing the same voltage, and they all have the same resistance. So V squared over R is the same for all of them. So kind of surprisingly, they're equally bright. You might wonder, aren't we getting something for nothing if we can just keep adding bulbs and just get more and more light out? And what we're doing, of course, is drawing more out of the battery, because the power draw in the first case was just v squared over r, but the power draw in the second case is 2v squared over r. So we do get more light, but that's because we pay the price of having more energy. All right, what happens to bulb A when the switch is thrown, when the switch is connected? Well, again, when we throw the switch, C comes into the circuit, and then B and C are in parallel. We can see that pretty easily, I think, right? They are a parallel thing. And so this thing gets replaced with some equivalent resistor, or bulb, really resistor. And now we have what A was, plus the equivalent going into the EMF source. But we know that this is less R. Again, we've taken two things in parallel. We know that their combined is a lower resistance. So the whole circuit has a lower resistance, so we're drawing more current. But if we draw more current and we run through A gets brighter. All right, to kind of sum up things we've seen here, we've had resistors and capacitors, and they can each be added in either series or parallel, and the equations look very similar, but not quite the same. You can see the pattern in this chart. Resistors in series simply add, and capacitors in series add by reciprocals. And then the reverse is true for parallel. Resistors in parallel add reciprocally, but capacitors in parallel add directly, which is sort of annoying. I have to tell you, the way I remember this is I actually remember this one. That resistors simply stack, because I can think, oh, the longer the path, the harder it is to push the electrons through. And then every word you change is a flip. So when I say change from series resistor to parallel resistor, I flip to reciprocals. And if I change from series resistor to series capacitor, I flip to reciprocals. But if I change from series resistor to parallel capacitor, that's two flips, and I'm back to where I normally would have, just having them add. I don't know if that's useful for you or not, but that's how I remember it. Why is it that they look almost the same but not? It ends up coming down to that we've defined the voltage in terms of the charge is something times the voltage for capacitance, but we've defined it that the current is the voltage over something for resistance. And that's really what causes that interpretation. If either of those had been defined the other way, these would have the same add. Most especially if we worked with conductances instead of resistances, then everybody would add the same way. But historically we don't, and so we're kind of stuck with this bit of awkwardness. What is the battery current drawn in this circuit? We're going to want our equivalent resistance. So 1 over the equivalent resistance is 1 over 12 ohms plus 1 over 6 ohms. So it's 1 over 12 ohms plus 2 over 12 ohms, which is, of course, 3 over 12 ohms. That's 1 over the equivalent resistance. So the equivalent resistance is the reciprocal of that, which is 12 thirds ohms, or 4 ohms. Not what they asked for, though. They want the current, and the current will be the EMF over the equivalent resistance, so it will be 12 volts over 4 ohms, or 3 amps. Find and label the current through each resistor. I'll be honest, my first instinct would be to find the equivalent resistance so that we could find the current that's drawn, and then have it split into each of these. But that's kind of silly, because we know for each of them, between here and here, for instance, the current through the 15 ohm resistor is going to be the voltage across it, which is 9 volts over the 15 ohms. And likewise, the current through between here and here on the 4 volt one is going to be 9 volts over 4 ohms, so 9/4 amp. And finally, the current through the 8 between here and here, say, is again 9 volts over 8 amps, or 9/8 of an amp. If you grind it out with the equivalent resistor, you find that, in fact, the current that comes out is the sum of those three things, which is the crazy value of 159/40 of an amp. But You don't need to do that. It's a lot faster to just go through knowing that the voltages are the same. All right, the light bulbs are identical. Initially, both bulbs are glowing. What happens when the switch is closed? Okay, when the switch is closed, then we have something very interesting. We have a path with no resistors in it, and remember the wires are assumed to be resistanceless. So this is essentially a resistor of resistance 0, and that leads to something kind of weird. The equivalent resistance for the circuit is 1 over 0 plus 1 over the resistance of B, which is, of course, infinite. So the equivalent resistance of these two things is 0. So that there is essentially no resistance between here and here. No equivalent resistance, which makes sense because when the current comes out of the battery, it goes through A, and then it takes the path of least resistance, which is clearly this. And so all of the current goes this way, and none goes that way. Which tells us two things. One, B goes out. There is no current through it, so it does not act anymore. And that's enough to tell us that it's answer E. But we can also say that because the resistance used to be A and B, and now it's just A, the resistance has gone down, so we draw more current. We're pushing more current through A, and so A gets brighter. Here, all the bulbs are identical. Circle in blue the letter or letters of the brightest bulbs, and circle in red the letter of the dimmest bulbs. All right, our very first thing to notice is that clearly C and D will be the same. So if one of them gets circled, the other one has to get circled as well. We also look at this and say, well, the current, by the current law, the stuff that's going through A splits through into B, right? So we call this IA, IB, and I'm going to call it IC. And clearly IA is greater than IB, or we'll say and IA is greater than IC. So A is going to be the brightest because it's getting the most current. Now the resistance of this branch is half the resistance of this branch. C and D are in series, so their resistance simply stack. Since it has half the resistance, it's going to get twice the current. So IB is greater than IC, which means that B is brighter than C. But that means that B is the middle child here. C is less, and because C is less, then we know that D is less as well, and so we end up with this pattern.